Okay, so let's continue. To recall, what did we do? Let a be a positive real, let m and be integers and greater than 0. Okay, first we'll recall what our original goal was. So we started with let with a greater than 0. So given a greater than 0, can we define powers a power r, where r is rational? So we want to define powers a power r where r is any rational. So first we considered the simpler question. Let a be greater than 0, let n be a positive integer. Can you define the power a power 1 by n? Then we gave the definition. Let a be positive, let n be a positive integer. The unique positive real such that box power n is a is defined to be a power 1 by n. And by a theorem which will not prove, a power 1 by n for a positive and n positive integer always exists. So the unique positive real box such that box power n equals a, it always exists, and that is defined to be a power 1 by n. Then we asked like how can we use this to define a power m by n, where m and n are integers and n is greater than 0. Then we defined a power m by n to be, so let a be greater than 0, let m and be integers and greater than 0. Then we defined a power m by n to be the nth root of a power m. So this definition was because, so we try to mimic the definition of m by n to get the definition of a power m by n, and then we rewrote the definition in this simpler way. If a is a positive real and m and n are integers, n is positive, then a power m by n is defined as a power m power 1 by n. So any positive number power 1 by n is already defined and it exists by a theorem which will not prove. So nth roots exist. We will assume that nth roots exist. Nth roots of positive reals exist. So a power m by n is defined to be a power m power 1 by n. Then we showed that this a power m by n is actually can also be written as a power 1 by n power m. So it's the mth power of a power 1 by n as well. So this is the summary of what we have done so far. So let a be positive, let m n be integers n greater than 0. Then a power m by n is defined as a power m power 1 by n. And we found out that this quantity is also equal to a power 1 by n power m. So let's continue. Let a be greater than 0. Let r be a rational. So we can ask, how can we define a power r, or how can we compute a power r? So a is positive and r is an irrational. So how can we compute a power r? So first step what we do is we pick a representation. So we defined a power m by n, where m and n are integers and n is greater than 0. Hence we first pick a representation r equals m by n, where m and n are integers, n is greater than 0. So after picking the representation, we compute a power m by n, which is a power 1 by n power m. We saw that a power m by n is also is a power m power 1 by n, and it is also a power 1 by n power m. We saw this. So we'll compute this quantity, and then we define a power r to be this quantity a power m by n we computed above. So in this process, we can ask, does so how can we compute a power r? We are saying this is the process for computing a power r. So we need to ask, in the above process, is a power r independent of the representation of r we pick? So we have defined a procedure to compute a power r, but we need to check, is this procedure actually give the same, does this procedure give the same answer when we pick different representations of the same rational r? Do we get the same quantity? So here's the observation. So this shows that a power r is well defined. A power r as defined above is well defined. So let a be greater than 0. Let r be a rational number. So consider, suppose you pick two representations. So pick representations. So r equals m by n and r equals p by q. So n is greater than 0 and q is greater than 0. N is a positive integer and q is a positive integer. Pick two representations. Then in the above procedure we are to output a power 1 by n power m, right? So in whether we compute a power 1 by n power m or whether we compute a power 1 by q power p using the representation p by q of r, we get the same result. Hence a power r as defined by the above procedure is well defined. So let a be greater than 0, let r be a rational. Pick representations r equals m by n and r equals p by q, where n is positive and q is positive. Then the quantities which we output. So a power 1 by n power m and a power 1 by q power p both are same. So we'll prove that. So first note that a power 1 by n power mq, what is this power? This power is a power 1 by n power. So m by n is p by q, right? So mq is np, right? So this is equal to a power p, right? So a power 1 by n power mq is a power p. Hence we can write a power 1 by n both. So a power 1 by n power mq, we can write it as qth power of a power 1 by n power m. This is a power p. Hence a power 1 by n power m acts as a power p by q. Hence we get that a power 1 by n power m is equal to a power 1 by q power p. So we showed that using basic intuition that a power 1 by n power m and a power 1 by q power p both are equal. So here we used a crucial property. Hence, so this is because a power mn is a power m power n for a greater than 0 and integers m and n. So we can show this. So this is intuitively true, right? For example, a power minus 6 is a power minus 2 power 3. It can also be written as a power 3 power minus 2 and so on. And this is intuitively true if you think about it. So we use this property, and hence a power 1 by n power mq, we wrote this as successive powers, a power 1 by n power m power q. So we use the above property, power of product. So this is a power of product, not power of product. So you can call it a raised to product. So this is more or less the result we used. And so a power 1 by n power mq, we wrote this as a power 1 by n power m power q. So m and q are integers and we can write that. Hence we found that a power 1 by n power m actually acts as a power p by q. Hence a power 1 by n power m is equal to a power 1 by q power p. So hence what did we find? Hence, so a power r a power r. So a is greater than 0 and r is rational, is well defined. How do we define a power r? We define a power r by this procedure. We first pick a representation of r in terms of m by n, where m and n are integers and n is greater than 0. You can pick any such representation. Then you can compute a power 1 by n power m, and then that output a power 1 by n power m is defined as a power r. So we showed that irrespective of what representation we pick in the process, we get the same output. Hence the above a power r is well defined. So we showed that a power r is well defined. Now we can ask what are the properties of a power r, right? So we can ask, let a be greater than 0. What are the properties? What are the properties of powers of a? So we can ask a more specific question. How does taking powers, or it's not a specific question, but we can ask, how does taking powers interact with addition and multiplication of rationals? So this is a valid question. How does taking powers, we came across this new operation, right? We came up with this new operation, taking powers. How does this new operation interact with the existing operations of addition and multiplication? So we have an observation. There are a few basic properties of taking powers. First one is a power r1 plus r2 is a power r1 times a power r2. We'll see this. So let a be greater than 0. Let r1, r2 be rationals. So then what we have is a power r1 plus r2 is actually a power r1 times a power r2, right? So we'll prove this. So for proving this, we first pick representations. So we pick representations r1 equals m by n, and we pick a representation of r2 p by q. So n is positive and q is positive. So all right. So first pick representations of the rationals r1 and r2. Now note that what is a power r1 plus r2? So a power r1 plus r2, this is just a power, so m by n plus p by q, right? So this we can write, and then we can write this as, it's just nq, and so qm plus np, right? So qm plus np by nq. Then by the, so we can write this as a power 1 by nq by the definition of a power m by n, a power 1 by nq power qm plus np. So we found that a power r1 plus r2 is this quantity, a power 1 by nq power to the power qm plus np. Okay, so now we need to check the other quantity. So a power r1 plus r2 is this. So note that a power r1 times a power r2, what is this? A power r1 times a power r2 is a power m by n times a power p by q, right? So now what is a power 1 by n? We can write a power 1 by n. We saw that we can write a power 1 by n as a power 1 by n power m, and we can write the a power p by q as a power 1 by q power p. So this we can do. Then we can further write a power 1 by nq. So you can take q times this whole thing power m, and you can take n 1 by nq, a power 1 by nq, this whole thing you can take, n and q are positive, right? N and q are positive, so you can take n times and q times. So this is true. And then so mth power of product, we saw that it is the product of mth powers, right? So a power 1 by nq power q power m, right? So a power 1 by nq power q power m. So a power 1 by nq power n power p. So we know that we saw that above, we saw that a power mn is, so a raised to product is a power mn is a power m power n. So we can write, we can simplify this as a power 1 by n cube power qm and a power 1 by n cube power np, which is just a power 1 by n cube power qm plus np. So now note that this quantity a power 1 by n cube power qm plus np and a power 1 by n cube power qm plus np both are equal. So hence we showed that a power r1 plus r2 is in fact a power r1 times a power r2. So this is a great identity. So power of sum is just a power r1 plus r2 is just a power r1 times a power r2. This is a very useful observation of powers of a. Right, we have another observation. How does taking powers interact with, say, multiplication? So we have observation. So this is a power r1 times r2. What is a power r1 times r2? It turns out we can write this as a power r1 power r2. So let a be greater than 0. Let r1, r2 be rationals. So then it turns out a power r1 r2 is just a power r1 power r2. So this is another useful property of taking powers. So note that these properties already hold for integer powers. So we can easily verify a power m plus n is a power n times a power n, and a power mn is a power m power n. We can easily verify these for integer powers, but it turns out these properties extend to rational powers as well. So we'll prove that. So we'll prove that a power r1 r2 is a power r1 power r2. So proof. As usual, we first pick representations. To compute the quantities, we need to pick representations. So pick representations. R1 equals m by n and R2 equals p by q. As usual, n and q are positive integers. So once we pick the representations, now we can note that what is a power r1 r2. So a power r1 r2 is just a power m by n times p by q. This is just a power mp by nq, right? So this is just a power 1 by nq power mp, right? So a power r1 times r2 is this. Now note that a power r1 power r2, we can compute this as well. So a power r1 power r2 is a power m by n. So this whole thing power p by q. So a power m by n, we can write this as a power 1 by n power m, and then this thing power p by q. So now what we can do is we can do an interesting thing. So we can further break down. So a power 1 by nq power q. So this whole thing is a power 1 by n. This whole thing power m power p by q, right? So each a power 1 by n term. So this a power 1 by n term, we can write this as a power 1 by n 1 by a power 1 by n cube power q. So we can replace a power 1 by n by a power 1 by n cube power q. That is there, that we can do. Then so we can treat a power 1 by nq as a box. So in putting a power 1 by nq in a box, we see that power q, power m, power p by q. So this is just box power q, power m, power p by q, right? So we call a power n by q as box. So a power box power q power m is box power qm. So we can write mq, box power mq power this p by q. What is this power p by q? This is by definition box power mq power 1 by q power p, and box power m by m cube times 1 by q is just, we know that this is box power mq by q. We noted by the definition of a power m by n. So a power m power 1 by n is just a power m by n. So this power p. So we can cancel q here, and then so box power mp. So we simplified a power r1 power r2 as box power mp, which is just a power 1 by nq power mp. So now note that a power r1 r2 r1 times r2 is a power 1 by nq power np, and even this quantity a power r1 power r2 is a power 1 by nq power mp, right? It's just playing with powers, right? So both quantities are a power 1 by nq power mp. Hence a power r1 times r2 is equal to a power r1 power r2. This property, which we know holds for integer powers, also turns out to hold for rational powers. And then we can look at another property. So another observation. So this is power of product AB, or let's start with a question. So we asked AB power 1 by n is a power 1 by n, b power 1 by n, when AB are positive and n is a positive integer, right? We saw that. So we can ask, let AB be greater than 0, let R be a rational. So this is the power of product. We can ask the same question which we asked for AB power 1 by n. Can we express AB power R in terms of, suppose you know a power R and b power R, can you find rth power of the product AB? So it turns out there's a very simple relation like we had for nth roots. So observation is, so AB power R is a power R b power R. Let AB be greater than 0, let R be a rational. So AB power R can be computed by multiplying a power R and b power R. So what are the three properties? We saw that a power sum, a power r1 plus r2 is a power r1 times a power r2. We saw that a power r1 times r2 is a power r1 power r2. So power a raised to a sum and a raised to a product, we found some simplifications, and now we are asking product raised to a power, so ab power r. So we found we can show that ab power r is a power r b power r. We will prove this. So proof is, pick a representation of r, right? We need to pick a representation of r. Pick a representation r equals m by n of r, so n is positive here. Now note that what is AB power R? So AB power R is just AB power m by n, right? So this is just AB power 1 by n power m. But we know that nth roots, it kind of, we can write this as a power 1 by n times b power 1 by n, this whole power m. Hence we can, so this is a power 1 by n power m and b power 1 by n. So mth power of product is this. We used mth power of product rule. And then a power 1 by n power m is just a power m by n and b power m by n. So or directly you can write a power m by n and b power m by n, right? A power 1 by n power m, this is just a power r, and a b power 1 by n power m is just b power r. So we showed that ab power r is a power r b power r. So hence AB power r is A power r, B power r. So these are the basic properties of taking rational powers of a positive real. A power sum is A power r1 plus r2 is A power r1 times A power r2. A power r1 times r2 is A power r1 power r2. And finally, AB power r is A power r, B power r. Here the bases A, B, they are always considered to be positive reals, and the powers are always considered to be rational numbers. So these are the basic properties of taking rational powers of a positive real. So right, so these are the basic properties, and that's all for this part. See you in the next part.